It's working?
Yeah. Ready? You ready to click? Should I click for mine? Okay, great. So hey everyone, we are here today to talk to you about Patchflow, and that's the future of pipe repair. We came to this idea after conducting a number of future scoping sessions where we looked at today's trends and then took those forward 20 years to see what kind of world we could be living in at that time. We started with trends that were very specific to a certain area, but also kept in mind larger trends that affect the whole world. And so our specific trend, our so-called signal, was the fact that it's increasingly difficult to repair and maintain underground infrastructure, such as electricity and gas lines. And this is because of increased urbanization and the proliferation of fiber optic cables that are also underground, making it more densely populated there underground. And we wanted to combine this with the idea of climate change that will affect the entire world as we all know it. We initially wanted to create a system that would allow for a unified integration of underground infrastructure so that all the systems could be repaired together more efficiently. But we realized that this was far too costly in terms of retrofitting existing systems. So as such, then we decided to move on to a system that would allow for use in current infrastructure. And then water networks were deemed to be an ideal place to start because of how impacted water will be by the future of climate change. And so to give an example, a more specific example, the leakage problem in London is absolutely huge. Thames Water, and that's London's main drinking water supplier, leaks 693 million liters of water each day, and that's 8 million bathtubs worth for a population of 9 million people. This is in large part due to aging infrastructure, much of which is still from the Victorian times, with pipes that are over 100 years old. The second issue is the economic perspective. Each leak that requires to be fixed requires approval from the council for roads to be closed, 3 to 5 days of hard manual labor from teams, and intense work. This will average the cost of a leak repair to around £3,000 then. According to a leakage expert from Wessex Water as well, only the most disruptive leaks are actually able to be fixed because a lot of the smaller leaks, there's just not enough manpower to be fixing those. And of course, this issue is not isolated to London, and in the US, there's an average of 6 billion gallons of water about each day that's lost due to leaks throughout the water network. So this is certainly a global issue. And then, of course, climate change we want to come back to, and that's going to be a huge impact on water accessibility in urban areas. And in future, increased drought frequency will make water leakage a more acute problem as supply becomes lower. And at the same time, these extreme temperature fluctuations will result in the soil that surrounds the water, surrounds the pipes, fluctuating in size. And this will increase the load on the pipes and crack the pipes more often, leading to more leakage, which we already saw in London in this summer of 2022. And this, combined simply with the networks getting older as they're not repaired, will lead to an estimated 10 to 15% decrease in the amount of water available in England. And at the same time, while water is getting harder to come by, we also expect rising urban populations to increase the demand on the network. For example, North London alone is expected to require an extra 265 million liters of water for its increased population per day by the year 2045.
Okay, so yeah, as Owen said, we chose Thames Water, and the primary reason we chose them is because they've got the largest distribution network made up of cast iron pipes over 150 years old, and this becomes really prevalent when you're talking about degradation to these pipes. As past this age, you sort of get lots of leaks amongst this. Now, innovation is forced upon Thames Water by governmental bodies like Ofwat and DEFRA, and this innovation can be sort of summarised into 3 different sections. The first is providing clean and uncontaminated drinking water. The second is avoiding interruptions that are greater than 3 hours. And the final one is to cut leakage by half by 2050. So how are Thames Water trying to approach this? Their main method at the minute is to prolong asset lifetime by implementing polyethylene sleeves into their pipes. And these are great because they're resistant to the familiar forms of corrosion that cause cast iron pipes to decay. And so they remain with that structural integrity from cast iron while still remaining sort of corrosion resistant to chloride ions that cause corrosion. So then this is okay, but the problems with because the water industry has such low margins, it means that they only manage to get at most a 1.8% turnover per annum, whereas the real figure is much closer to around 0.5%, which means they're looking to replace the entire network over a stage of sort of an extra 200 years, which isn't a viable solution at the minute. They need to roll this out faster, so more work needs to be done. Another area which they're looking at is trying to implement sort of predictive and prescriptive models to model the pressure and transients flow within the network. And this is good because it's actually reduced leakage by 10.7% between 2022 and 2023, which is really effective. However, they're still losing huge amounts of water, and they've been trying to find an excess of 120 million pounds by Ofwat for not achieving their targets for leakage reduction. So what they're actually doing about it. So current research mainly focuses on leak location and identification and finding leaks within the network. And this is useful. However, it actually only accounts for around 20% of the cost of repair. 80% is actually in the repair itself. So this is where we thought we'd be able to bring some impact and some innovation to the network. So we're introducing Patchflow. So Patchflow is a semi-autonomous invasive robotic solution that can enter the pipe stream and passively flow downstream and expand and apply composite patches to leaks. And from there, this means if you attack the minor leaks initially, it stops and prevents them from becoming larger leaks, which both prevents leakage currently and in the future. So it works on two fronts with Thames Water. So take a look at our process. So the first step is for a technician to approach an access point where they'll insert the device into the stream, where it will start to flow downstream. Once it's reached its predefined rough location described by the prescriptive model we were talking about earlier, it will expand its initial anchor, followed by a secondary anchor which isolates the crack location. And once this is isolated, it infills it with a resin composite, and then after that, it then flushes the entire crack with soft robotic actuation, which then forces any debris through the crack out and also forces the resin composite into the crack itself. And this is really useful because it also limits the surface area of the composite material to the water, which is really important for mitigating the risk of contamination, which is one of the most important features for DEFRA. And finally, once cured, the robotic detaches from anchors detached, and it flows downstream to a trap where it's extracted at another access point by a technician.
Great. So yeah, in terms of the economic impact then, so very recently in the news in the UK, there's been a lot of controversy about raw sewage leakage into the country's waterways. And because of this, the water companies have asked for an additional expenditure of doubling their expenditure to £96 billion in the period from 2025 to 2030. And this will be to fix sewage leakage, drinking water leakage, and to increase capacity by adding new reservoirs. But this is obviously controversial, as the bill in the end will be footed by the consumer of the water, just everyday people, who will have to pay on average an extra £156 on their water bill per year. And so the responsibility of for the economic aspects of the network is covered by Ofwat, who regulates this. And they're the ones that are responsible for setting leakage targets, but they have to make sure that these remain reasonable and sort of don't increase the cost of water bills too heavily. So, and this phenomenon is known as the sustainable economic level of leakage. So for example, if you wanted to fix leakage entirely, you could dig up all the pipes in London and replace them all, but then people would be paying tens of thousands of pounds on their water bill, which is just not possible in the current economic climate, of course. And then this means for us that decreasing the cost of leak repair does not decrease the overall market size, because we're not limited by the cost or the amount of money. We're limited simply by the number of leaks we can fix economically. And in terms, another interesting stat, in terms of boots on the ground doing the actual work, for Thames Water, there are only currently 240 leakage repair teams that serve the entirety of the network. So that's over 9 million people served by only 480 million people responsible for locating and fixing all the leaks. And so we need to improve these teams' efficiency. And to do that, this is why our system was invented. And then even further in the future, our system could possibly be even more autonomous and even completely autonomous to even further increase the number of leakages that can be repaired. And so what we're doing now is obviously a very futurist idea, very far in the future. So what we're doing now, our upcoming development, is we're looking into focusing our master's projects on this area. And so I personally will be looking at this one on the left, automating soft robot creation with smart casting, as I think that soft robots will definitely be a big part of the future. And of course, definitely in water networks where you don't want to be damaging the pipes.
So yeah, in addition, I also have a smaller project looking at how we might be able to infer information about pipe lifetime from vibration data that's fed down the cast iron pipes. And a larger project I also have is to do with our sort of first development stage, which is inserting a tethered device into the pipeline and then letting it expand and leave like a shell behind for a repair. And and then being extracted from the same entry point. So the main vision of our system is to have water be seen as the valuable source it will be, and for this to be realized, it's going to take a while and lots of innovation from different sectors within the water. And we feel like we're going to be able to be in that transition stage from this sort of traditional old unintuitive network we have to this smart network in the future, which will hopefully enable us to have a secure water supply in the future, even when there's less supply of it in the environment. Thank you for your time.